Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Yes, you're in Math 1108. Let us. Boop. Okay, there we go. All right. Okay, so we did some probability teasers last time. I want to begin the class by going over the solutions to a couple of them to kind of showcase some of the techniques that we will be looking at in the future, as well as kind of to segue into the next topic, which we're just going to scratch the surface of today, but we'll get more into it next week. So next week, the majority of the week will be spending on learning how to count. A lot of people think they know how to count, but a lot of people are wrong in that regard. So we're going to learn how to count, because counting, as you'll see when I'm going through these examples, it's going to be a very important thing to be able to do. So the majority of our time, if not all of next week, is going to be on us learning how to count, because I'm going to teach you the techniques, but also I'm going to want to go through a bunch of examples with you guys. And I guess it's just a matter of how quickly you catch on. Potentially Friday, we can start probability if we get through all the problems, but I wouldn't rush it if that is the case. Yeah, so that's where we are. So what we're going to do now is to just go through some problems. So the Monty Hall problem, very famous problem, notoriously, it's one of those problems where notoriously people just didn't believe the answer. But hopefully I'm going to convince you today mathematically that the answer was correct. So the Monty Hall problem, just to remind you, you're on a game show. There are 3 doors. You get to pick a door and you win the prize that is behind the door. So there's one main prize, which traditionally is a car. There are 2 other prizes, which traditionally are goats. I don't know why they picked goats, very random, but they did. And so you want to win the car. So you pick a door, and Monty does something very, psychological. He tries to psych you out. He opens another door and he says, oh, looky here, there's a goat. Maybe the door you picked has a goat behind it. Do you want to switch your answer? Do you want to change doors? And the question, the $64,000 question, or the brand new spanking brand new car question was, should you switch doors? Should you switch? And the answer was, yes, you should switch. So the answer was yes, which was very surprising to a lot of people. It was very surprising to you guys. I believe most of you put no in the chat. And if I were to guess why you put no, one, it's like, you probably think maybe he's trying to psych me out. Maybe I got the car. Another thing you might be thinking is that, well, I mean, I have a 50-50 chance now of being on the car, right? So it doesn't really matter if I switch. And so why am I going to waste my effort to switch? I'll just stay and see, I could be lucky. It turns out though, mathematically switching is the best option, and you should always switch if given the choice. Now let's actually see why that is. One way to see this is to actually draw it out. And draw a diagram. It's a very common technique. At least at this level. Explore later. There are many kind of diagrams you can draw. There are tables. There are what we call tree diagrams. There are all sorts of diagrams. But you just want a diagram that allows you to really think about the problem so you can actually see what the moving parts are. And so we can use a diagram. So here, suppose you pick this door, and Monty opens this door. I'm going to put it on the diagram. You probably don't know what those doors are yet. It's going to be on the diagram. Okay. So here's that. 3 doors. I'm going to look at 3 different cases. Also, C is the location of the car. And what I'm going to do now is I'm going to measure whether you win by switching or you lose by switching. So you have 2 options. The choices you have are, you should either switch or you should stay. Now, a lot of you felt like you should stay, but let's actually just see if we should have stayed, right? So for the purpose of this illustration, I'm going to pretend that the car is behind door number 3. However, the exact same argument could be used if it was behind any other door, right? So let's say, you know, multiple timelines is actually a thing, and let's actually play out all the scenarios that can happen in this case. So you're on this game show. The car is actually behind door number 3, but you don't know that. Monty knows that. So he says, hey, pick a door. You go like, I picked door number 1, Monty. Okay. Monty goes, oh, you picked door number 1. Lucky number 1, huh? So you know what? Yeah. He opens this door and shows you a goat. Then he asks, do you want to switch your answer? Now, what would happen if you switched? Well, you would win the car, right? Because the door you were on doesn't have the car. So if he scares you now and you switch, you would win the car. If you stay, you're like, nah, it doesn't matter if I switch, you would lose. Okay. All right. Let's look at another alternative timeline. There's a different version of you in a different universe. Monty asks that version of you, pick a door. And you go like, door number 2, Monty, right? You could have made that choice. That was possible. Then Monty goes, okay, look here behind door number 1. There's a goat. Do you want to switch your answer? And what would happen if you switched your answer? Well, you're not currently on the car. So if you switch, you would be on the car. So yet again, in this universe, you won the car. You would lose by staying because you picked the door that doesn't have the car. Now, alternative timeline. There's a third version of you who is given this choice. Monty goes, pick a door, any door. You will win the prize behind the door you pick. And you go, you know what? I picked door number 3, Monty. Now, Monty can open any one of the other doors because they're both goats. But let's say he opens door number 1. Oh, look here. There's a goat. Do you want to switch your answer? What would happen if you switch in this case? Well, you are on the car. If you switch, you lose. However, if you stayed, you would win. Now, the question is, should you switch or should you stay? But look at what happened here. In the switch scenario, you win 2 out of 3 times. It's not a guaranteed winning strategy, but it's the better strategy, clearly. Here, you only win 1 out of 3 times, right? Switching is better. Right? Like, not because of feeling or because we don't trust Monty or any of that. Like, Mathematically, it's better. Draw out the diagram, draw out all the possible scenarios of all the choices. No matter what you say, he's going to show you some other door, right? Whatever his agenda is does not matter, right? Whether or not you pick the car, he will show you another door just to psych you out, to make the game exciting, to increase ratings, right? So this is going to happen anyway. Whether or not he's trying to psych you out is irrelevant. Whether or not he realizes that you got the car in the first place or not is irrelevant. He's going to open another door and show you. 2 out of 3 times, it is in your interest to switch. Should you switch? Yes, you should switch, right? And that's clear because of the diagram. There's another way to look at this. Is to use there are many ways to look at this, by the way. So I believe the problem is famous. So I believe there's even like a Wikipedia article on this where they talk about a bunch of different strategies for actually thinking through it. I'm giving you guys like the 2 most famous ones, or the 2 most common ones. Use the opposite of what good math thinking tends to be. Sometimes you have to think outside the box or think outside the door and make the problem harder, right? Now in math, often what we do is when we have a very big, difficult problem, we make it easier, we make it simpler. We try to figure out the solution in the simpler case, and then we extrapolate it to the harder case. So if you have a problem with 10,000 moving parts, what a math person would tend to do is imagine that there are only 2 moving parts, or there are only 3 moving parts. What would the perfect answer look like in that situation? Then they might bump it up to 4 or 5 moving parts just to see if there's a pattern that they could figure out, and then eventually become clear. Yeah, if I had 10,000 moving parts, this is the strategy that I would use. It's going to work. Here we're going to do the opposite. Here we only have 3 moving parts, 3 doors. Let's make it harder. Let's get more. Suppose trying to get the scale right here. Suppose there were, I used 1,000 doors in the other class. Let's just use 1,000,000 doors. A million. Right? Suppose there was 1,000,000 doors. You're on a game show. They have a lot of real estate. 1,000,000 doors on this stage. So there's a door, there's a door, there's a door, dot, 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 door, door, dot, 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 dot. Okay. There's a door, there's a door, there's a door, dot, 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 door, door, dot, dot, dot. There's a door, there's a door, there's a door, dot, 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 dot. Okay, so here we have 1,000,000 doors. Monty asked the question, pick a door, any door. You will win the prize behind the door you pick. You say, I pick door number 1, Monty, for argument's sake, right? So let's actually think through what this would actually mean. So you pick the boom, that should be red. You pick the door. I want you to consider right now, what are the chances that you picked the car? Maybe someone can tell me. what is the probability that you pick the car?
Is it 1 in a million?
1 in a million. You're 1 in a million, right? There's a 1 in a million chance that you're right. 1 over a million. Better odds than the lottery, but still not very great odds, right? Chances are you're wrong, right? Chances are the car is behind another door. Right? Now, Monty opens, represented by the blue X, all but one door and asks if you want to switch. Someone's trying to get in here. I think they got dropped out, right? So you've said, I picked door number 1, Monty. Now remember, chances are you're wrong. There's a 1 in a million chance that you have the car right now. Chances are the car is somewhere else, right? Monty goes, look at this. Goat, 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 goat. He opens every option except one. Shows you that they're goats. This whole time you're freaking out. You're getting like, oh my God, there's so many goats. I've never seen so many goats in my life. Like this is a lot of goats. Like what if I have, I don't know, is he trying to trick me to switch? And so, you know, at this point, you're like, oh my God, there's so many goats. You're freaking out. Now, Monty asks you to switch. Do you want to switch? He says. Hell yeah, I want to switch. Of course I want to switch. Why wouldn't I want to switch? There was a 1 in a million chance that I was right. There was a 999,999 over a million chance that the car is somewhere else. Now you've isolated that somewhere else to one other option. Yeah, I want that other option, right? There's a 999, right? Like there's a 1 in a million chance of car. Now here, there's now a 999 over a million chance of car, right? Chances are you are wrong. Chances are the car is somewhere else. Now there's literally only one somewhere else. Do you want to switch? You betcha I want to switch, right? Like more than likely I was wrong in the first place. I should switch if given the option, right? Now it's kind of obvious when you have a million doors, but the truth is that same thing holds true when you have 3 doors. What were the chances that you picked the car on the first try? 1 out of 3. There were 2 out of 3 chances that you were wrong, right? It's more likely that the car is somewhere other than what you picked, which means if a lot of options are eliminated and you're asked, do you want to pick something other than what you picked? Yeah, you should jump at that chance because chances are the car is somewhere other than where you picked, right? So for some people, like seeing it that way really makes sense. Like, yeah, I mean, there really was like a 1 in a million chance that I was right in the first time. Yeah, I would switch to another door. Some people like the diagram where they can actually see, okay, win, lose, win, lose. Okay, yeah, there are 2 wins. There are 2 wins here, and there's only 1 win over there. It's definitely better to have these 2 wins than that 1 win, right? And so that's the Monty Hall problem, right? 2 of the most famous solutions, but they all come from coming up with a clever diagram to kind of synthesize the situation so that you can actually really count your chances, right? 2 out of 3 chances you would win by switching. The best option is to switch. Let's go back to the 2 girls problem. Now, all of these had different answers. I believe I told you this one was 1/4. This one was 1/3. This one was a half. And this one was 13/27. That's going to be an interesting one. But for this one, it would be kind of weird to draw a diagram. Like, what diagram are you going to draw? 2 kids frolicking in a yard under a smiling sunshine as a finger painting with, oh, here's mommy and daddy. Let's put it on the fridge. Like, what would you draw in this case? Like, what is the diagram, right? There's another way to think of this. Think of the total possibilities as a set of things that can occur. Right, so here, total possibilities. Or, I don't know, let's call it options as well, because it'll be shorter to write. I can conceptualize them as a set of things. Now, there is such a thing as a set of sets. For example, we've seen the power set before, which is a set of sets. So now the question is, a set of what things would be useful here? It turns out that a set of sets would not work. So if I look at a set of children, like as boy, girl, that's not going to really make sense, because if I had 2 boys, the set would just ignore one of this information. You'd lose information. You wouldn't be able to tell who's the older child or the younger child, which one of these questions clearly brings up, the older child. So it's not really great. You want to take order into account, and you want to not ignore repeats. Sets do not take order into account, and they ignore repeats. So if you had 2 children of the same sex, a set would kind of look at it as just you had 1 kid. Not great. There was another object that we looked at where it does take order into account, and it does care about repeats. And this was the thing called the tuple. So what I can do is think of the children that these people have as a set of tuples, right? So think of it as just a set of coordinates x comma y, where x equals boy or girl, and this is the sex of older child, and y is boy or girl, and this is the sex of younger. Right? In other words, this would look like, there are not that many options here, so I can actually write this all out, right? So what are the options? They can have 2 boys. They can have a boy and then a girl. They could have had a girl and then a boy, or they could have had 2 girls. Right? Those are all the options. There are only 4 options, right? Now we saw that probability was the number of ways we can get what we want divided by the total number of options, right? The total number of possibilities. And so here, what is the size of the total? There are 4 things in the total. You can count them right there. Now, what do we want? We want the event A. What is the event A? The event that they had 2 girls is what we care about, right? What is the probability that they have both girls, right? So an event for us, and this is something I'll define more when we get to probability, is just a subset of the set of total options, which now we know what a subset is since a couple of classes ago. It's a subset of the total options, right? So that's what an event is. A lot of people think of an event as an occurrence. When it comes to probability theory, an event is just a subset of the set of total options, right? So out of all these 4 options, the one I care about is this option right here, right? So yeah, so what is the size of what we want? Well, there's just one thing that we want to look for. So this means the probability of 2 girls is the size of what we want over the size of the total, which is going to be 1, which is going to be 1 out of 4. So that's why the answer in the first situation was 1/4. Now let's look at B. What would our total options look like in part B? In part B, we were told, you know that one of the children is a girl, right? What is the probability that the other is a girl? So here, this before we had this. But guess what? This is no longer an option. Because you see, that's not the case that one of them is a girl. They're both boys. It's the other cases in which one of them is a girl. So here you'd realize that the size of the total is going to be 3. And once again, the size of what we want, and we want A equals 2 girls. So this means the size of what we want is again 1. And so the probability of 2 girls, if 1 is a girl, is going to be 1 out of 3. Right? Because now my total options was reduced. Right? But just me kind of dissecting things this way, it makes it easier for me. Like I can just count and I can get to the answer. Counting is important. C. What happened in C? We're told that the older child is a girl named Freuda. Her name doesn't matter, but the fact that she's the older child is what matters. Right? So in part C, what are the total options now? Well, without any restriction whatsoever, those would be our options. However, we're specifically told that the first child, the older child, is a girl, which means these two are no longer options. Since older child is a boy. So now the size of our total changes. There are only 2 things that are total possibilities now. And we want the possibility of 2 girls, which means the size of what we want is 1, which means the probability that the probability of 2 girls, we will have more efficient notation for everything I'm writing down now, but I haven't introduced it yet. So right now I'm just like writing out everything in words. 2 girls if the older is a girl. Well, that's now 1 out of 2. Okay, and so that's why that is a half. So a lot of people might read these questions and they think they all have the same answer, don't it? At the end of the day, you're just asking me about if there are 2 girls. Why would anything change? Well, it changes based on our definition of probability. What the total options are changes in each case. D, admittedly D, this one is somewhat tricky. Now you might see what I did with these and you might even believe that, yeah, I could have probably come up with that and that's fine. For part D though, if you don't feel like you would be able to come up with this at this point, I wouldn't sweat it too much. Eventually, after I teach you about counting and I teach you all the strategies and you internalize the strategies, you would be able to come up with something like this. But for now, it might get a little tricky. For the including for the fact, can I say that? One reason why is that there will be overlaps. You must be careful to avoid. Okay, so you're going to see where these overlaps come when I start filling out the problem. So now we want to take the day of birth into account. Right? In part D, we said one of the children is a girl born on a Monday. So now we're throwing the day of the week into the mix, right? We do not know which girl birthday was given, so we will account for the birthdays of both children. So what does that mean? My total possibilities would be total, like the general total, would be a set of things that look like this. I would do 4 coordinates, W, X, Y, Z, such that 2 of these letters are keeping track of the sex. The other 2 are keeping track of the day that the child was born. So W equals boy or girl equals sex of older. X equals the day older was born. Y equals boy or girl equals sex of younger. And Z represents the day younger was born. So in this scenario, we are told one of the children is a girl born on Monday. Right? So at the moment, we don't know which of them. We don't know, are you talking about the older child or the younger child? So we have 2 cases. Case 1. And probably you wouldn't have to explain all of this in like a test or anything. Like you'd probably start writing where I wrote case 1 or case 2. So one possibility is that the older child is the girl born on a Monday. We do not know about the second child. However, the second child can be a boy or a girl, and they can be born on a Sunday, a Monday, a Tuesday, a Wednesday, a Thursday, a Friday, or a Saturday. Right? So, but we don't know for sure. The other possibility is that they told us about the younger kid, that's a girl born on a Monday. The older child, though, we don't know about. This is a boy or a girl, and they could be born on a Sunday, a Monday, a Tuesday, a Wednesday, a Thursday, a Friday, or a Saturday. Right? Now, these 2 cases now represent all total possibilities. How big is that set of things? Well, here we have 2 options, boy or girl. Here we have 7 options. which means this is going to be a rule that I'm going to describe to you in a little bit. It's called the multiplication rule. Whenever you have several options to create a tuple, or several options for how the outcome of a stages of experiments, if you want to know about the total number of possible outcomes, you would multiply the number of options for each stage. So what you would have here is 14 total options. Similarly, over here, you'd have 2 options, and you would have 7 options. So there are 14 total over here. But be careful. There is an overlap. Notice that GM would be counted in both cases. Right? I could pick a G and an M here, and I could pick a G and an M here, and they would both show GM, which it's not really 2 separate cases. That's just one case. Both the older and the younger were girls born on Mondays, right? So the thing is, once I counted in one of these cases, I don't want to count it again in another case. So there's an overlap. So we will ignore this case. This means that the size of our total is going to be 14 plus 14 minus the 1 case that was ignored. And so that's 27. And so now you're starting to see where did that 27 in the answer come from, right? It wasn't just like a completely random number. So my total possibilities, my total options are 27 options. Now, what is it that we want? We want 2 girls. So what would that look like in case 1? In case 1, I already had a GM, but now I didn't have what was here, but now I know I want this to be G. I want 2 girls, right? So now the only thing that we have to pick is the day. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, right? So really, there are only 7 options to worry about now. Only 7 options. We know for sure we want a G in the 3rd position. Okay. Now for case 2, we know that the 2nd child was a girl born on a Monday, but now we also know I definitely want a G in the 1st position. So I no longer have a choice there. I want 2 girls, right? So which means the only thing I have to pick now is the Sunday or Monday or Tuesday or Wednesday or Thursday or Friday or Saturday. However, we'd ignore the Monday, because who likes Mondays? Ignore the Monday because it has an overlap with case 1. Right, case 1 already accounted for the fact that both children are girls born on Mondays. So what that means here is that you have 6 options. So this means what we want has 13, or in other words, it has 7 plus 6 equals 13 options. So now the probability of two girls if one is a girl born on Monday? Well, that's just going to be 13 out of 27. It's going to be the number of ways that I can get what I want divided by the total number of possibilities. Right, based on our definition of probability, like that's what it has to be. Which looks like a very strange answer until you actually work it out. But that is what it would be. And so, like I said, this one is a little bit tricky. You'd probably start writing your solution from here. But how to dissect this in your mind, how to actually count it, it's not really something I'd expect you to pick up on right away. By the end of next week, though, then yeah, I would expect you to be able to tackle a problem like this and figure it out. But that's going to be after I teach you some other stuff. But one thing that should be clear at this point, counting is important. At the end of the day, I had to create some set that described my situation, and then I had to figure out how many things were in that set, right? The set of totals is called a sample space, and the set of things you want is called an event. I'll describe these later on when we get to probability, so Friday into next Tuesday after next. I'll kind of define these terms for you, but it's clear that I need to know how to count. Most people think they know how to count. They're wrong. Counting is a very difficult thing, especially in a world like this where technologies and you have, you know, how many gigahertz your computer is running, how many gigabyte storage do you have? Giga is like already a billion. And you know, you'd have to count 256-bit encryption, like how many possible passwords can you have here and things of that sort. And you have to count like a lot of things. And you'd have to count into the billions, into the trillions, into more, right? The thing is, you want to be able to count efficiently. You don't want to have to be able to go at 1, 2, 3, 4, 5, right? You don't want to be able to have to do that because that will take you forever to solve any problem. The area of math that teaches you how to count is called combinatorics. So we are going to cover some very basic techniques from combinatorics for this class. Not everything you learn in a combinatorics class. Combinatorics is a whole class to itself because you need to learn how to count if you're going to be a math person, and most people just don't know how to count. So combinatorics, well, this is counting without actually counting, right? And counting, what most people think of it as is enumerating, right? What most people, well, not you guys anymore, think when they hear counting, right? They're thinking of enumerating, 1, 2, 3. Like I can count to 10 since I was like 3 years old. I can count, right? So everyone thinks they know how to count. What I want to appreciate is that what I did here was like counting like most people would count, enumerating. I wrote out all possibilities, 1, 2, 3, 4. There were 4 of them, and I could move on. Notice here, though, I did not do the same thing. I did not write down 14 options for each of these things and try to mix and match, well, GM, BT, GM, G, like I didn't list everything. I just knew how many things were represented here. I knew the answer was 14. I counted without actually counting. Of course, I counted with a sophisticated rule called the multiplication rule. And so there's a reason why I would count this to be 14, but I didn't specifically go through and go 1, 2, 3, and count up to 14, right? I didn't do that. I didn't list them out. I didn't do that. I applied a combinatorial technique, right? Which is called the multiplication rule in this case, which I'm going to describe for you very shortly, right? So that's what we're going to start to learn, how to count efficiently. And this leads to section 7.3 and 7.4 in our textbook, which is called Basic Counting Principles. /7.4 is entitled Permutations and Combinations. But I'm going to like cover them all at once because they're, at least I find there's a natural flow from one section to the other. So I'm not going to really think of it as two separate sections. I'm going to like do both sections at once and kind of flow from one into the other. But that's what we're going to do because counting is important and enumerating is not what we always want to do, not always. So I asked my other classes, so just for fun, I'll ask you guys. Do you guys know how long it would take to count to like 1 million if you counted one number every second? Take a guess, just any guess. It's just a fun factoid, so it's not, there's no consequences. Just take a guess. How long do you think it would take you to count up to 1 million? 1, 2, 3, 4, 5, 6, 7. You sat there and you just started counting. Right? Count roughly at one number every second. How long would you think it would take? What do you guys think? Just guess. Anyone has a guess? Are you guys actually working it out? Are you guys there?
Yeah.
Yeah.
Yeah, give me a guess. How long do you think it would take you? Give me a random time. It doesn't matter. Just throw something out there. Practice speaking up. What do you think? Just throw a number out there. It would take you a year. It would take you 5 years. It would take you 2 weeks. Would you be counting for a month? Like, what do you think? What do you think? Go on, throw out a guess. No one wants to guess. It would actually take you 11 days to count to 1 million, right? So less than 2 weeks, not as long as a year. It'll take you 11 days. To count to 1 billion, right, with a B, right? You know how long that would take? Well, you can actually calculate this as well, you know, multiply how many seconds in a day and in a year and blah, 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 and, you know, divide that into 1 billion. It would actually take you 32 years to count to 1 billion going 1, 2, 3, 4, 5, 6, 7, 8, 9, 32 years. So if you guys started counting from the day you were born, never stopped counting ever, most of you would not have counted to a billion yet. I don't think there's anyone here older than 32, right? So yeah, you guys would still be counting and you'd be like a significant way off, right? Like 10 plus years away from getting to a billion, right? So that's the kind of inefficiency we don't need, we don't want, right? I want you to be able to count to a billion very quickly. And so that's going to mean that we need some sophisticated rules. One of these rules is called the multiplication rule. Now I'm going to state it in 3 different ways and give a quick example. One way is more general than the other. I'm going to state it for 2 sets specifically, but then state it in general in 2 different ways. So here it goes. Suppose A, B are finite sets, right? The number of 2 tuples, and remember 2 tuples is just like a coordinate, A comma B, where little a comes from the set A, little b comes from the set B, that can be created is the size of A times the size of B. Tell me how many options I have for the first position, tell me how many options I have for the second position, and I multiply them. This is called the multiplication rule. This can be generalized if, let's say, A1, A2, A3, all the way up to AN are finite sets. The number of possible n tuples that can be created. So these are coordinates of A1, A2, all the way down to AN, where the A little I is from the big AI, right? So A1 is from the set A1, A2 is from the set A2, so on, right? That can be created. Is, well, tell me how many options I have for the first position. I'll multiply that by the options for the second, multiply that by the third. You can just keep multiplying by all the options, right? I'll tell you a third way to think about this. This can also be expressed as, in terms of experiments. If an experiment has m stages and you know that the number of options for the first stage is, say, N1, number of possible outcomes for stage 1. N2 is the number of possible outcomes for stage 2, ... N sub m is the number of possible outcomes for stage m. Right, so there are m stages, and I know how many ways each stage can go. You can think of creating a coordinate as that. Like this, there were 2 stages, and there's a certain number of ways the first coordinate can go. There's a certain number of ways the second can go, and I can multiply them. We can think of creating a coordinate as an experiment where we're creating stages. So now, then the total number of possible outcomes for the whole experiment is, well, n1 times n2 times n3 times ... times nm, right? This is called the multiplication rule. You just multiply the number of options for each. I'll give you a quick example. Suppose A is a set 1, 2, and B is a set little a, b, c. If I ask you, how many possible xy are there where x comes from A and y comes from B, right? Then one, by the multiplication rule, I know that the size of A is 2, the size of B is 3. So total possibilities is 2 times 3 equals 6. There's 6 total things. By enumeration, and I'll show you this because there are some times you want to enumerate. You want to just count it right away, and you don't want to have to worry about some clever way to count it. Just list them all. You can just list them. Here's one option. Here's 2 options. Here's a 3rd option. Here's a 4th option. Here's a 5th option. Here's a 6th option. 6 total options. Right? Sometimes you want to know how to do this, which is why I showed you this way of doing the problem, but sometimes you don't, because sometimes listing everything is going to be very hard, very cumbersome, takes forever. You want to know how to count things quickly, and so you would do that. So we'll stop there. We'll look at some nice counting techniques next time. So counting is most of what next week is going to be about. I'll let you guys go at this point. So yeah, thank you for your time and attention. I will see you guys in the next one. Ciao.